put together like a quick PowerPoint presentation on audio over IP. Basically, I started with what audio over IP is. So like a brief overview, some of the mechanisms that you need to know of how it works, and then I figured I'd try to focus more on like where it's used, because it's kind of the more interesting pieces of it. As like a precursor before I get started, I work at the Impact at the student radio station. And over the summer, I got to basically install one of these systems. I put it in 5 different studios. So since we have 5 different audio studios with one of these systems running in each one of them, and they're all networked. So it's kind of what got me into it. And then as I sort of understood it, when we went to AES last semester, I got to see a lot of the people that are using it in industry, and then they sort of like explained where it's going. And I think it's extremely interesting. So hopefully I'll get to talk about that and convey it to you guys. Before I get started too on that how does it work piece, I kind of glaze over some pieces, but if you're actually interested in this and want to know more, feel free to come up and talk to me after this. I'm doing some like basically startup stuff with the Impact on writing firmware drivers. So I know a lot on the computer side of it, and if you're interested in that, please come bother me. So here we go. What is audio over internet protocol? So basically audio over IP is a way of transmitting many different audio channels over long distances using a single Cat6e cable, so like an Ethernet cable. The transmission method is based on RTP streaming protocols and already existing like packet-based network architectures, so what you would plug your computer into in essence, like in the wall on an Ethernet cable. And then the whole reason why this is so great and revolutionary and a big deal is because traditionally, if any of you have any experience with live sound, if you want to plug in an instrument or a microphone, you have to use what's called a snake. And so for each one of these connectors, you have a twisted pair, so 2 wires plus a ground cable, and that's for 1 channel of audio. It's going to go through one of those connectors. So if you think about it, if you have 8 channels, like this snake is, you need to have a giant cable just to move 8 different microphone audio pieces. You need a new cable, in essence, like a new one of these connectors, every time you add a channel. So every time you add a stereo channel, that's 2 channels or 2 cables. So you need to keep adding pairs of 2 every time you add a stereo channel. So that's an analog snake, is what this is called. Now with audio over IP, in essence you can do, I think it's like 2 to the n, however big your bandwidth is, you can pick for audio over IP, you can use 1 single cable. So 1 single Ethernet cable, you can run many different audio channels over it, in both transmission and reception. For instance, with analog, you need 1 transmit cable and 1 reception cable. And with this, you can literally just have a Ethernet connection. So it is a very big deal for the broadcast world, and it's like specifically that's how I got into it, but it's also starting to get into the studio world and other places. So how does it work? The basics, take an analog signal at the far left, you convert it to a pulse code modulated signal. You do some signal processing on it. So for instance, if you want to do compression or EQing, you can do it all digitally. And then from there you do what's called RTP encoding, which I'll get to in a second. And then from there it sits in a buffer, and then from the buffer it gets served out into the local area network. And then from there, whatever's connected to your local area network can then receive it, sits in a buffer, gets decoded. You can do more processing on it if you want to for a specific application. Then it goes through another digital analog converter, and then it's back up to analog. So this is your sort of big block diagram process of what it's going to go through before you get to hear it on, for instance, a microphone to a headphone jack. From there, the first piece that you kind of have to understand, obviously, is sampling. So with audio over IP, it can support up to 96 kilohertz sampling frequencies with 24-bit depth, which is really high quality for a lot of the stuff that's being done with it. Like for instance, if you think about just a broadcaster microphone, that's actually really good. And then from there, once it's sampled, basically you take that bit, you have an actual sample, a single value, and then that gets sent in pulse code modulation to the RTP encoder. And from there, you create packets. So each one of these packets holds 64 individual samples, and then there's a header, and the header basically has what your standard internet packet has. So it has a MAC address where it was originated from, a channel number. So like there's a lot of different channels on each MAC address, so you basically can tell it which individual packet you're sending from. So like for instance, if I have a microphone that has its own channel number, if I have like a, like a CD player that would have its own channel number. It also sends the sample rate, the bit depth, what type of transmission encoding it's using, and then also the actual time. So that the global time that's agreed upon. And then there's just a checksum in the footer and a couple other things. But that's the basics of what you need to know for audio over IP. And then how RTP works. In essence, RTP is a protocol invented with the goal of streaming real-time data in a high bandwidth environment. So RTP stands for Real-Time Transfer Protocol. That's how you send those internet packets in basically a sort of realm where you can get away with like slower latencies and smaller sizes of packets, which I'll get to in a second of why that's relevant. And using RTP, that's like a sort of a standard that came about for any type of media streaming. So like it was for video, it was what people were using it for more often prior to audio. When AES 67 came out, which is the standard that the Audio Engineers Society came up with, it's built on top of RTP. So AES 67 uses the RTP protocol. The intention of AES 67 is all the people that are coming up with these different proprietary standards built it on top of RTP. That's kind of the basics of how the AES 67 standard came up. It's on top of RTP. If you want to know more about RTP, you can look it up. There's a ton of documentation on it. Same thing with AES 67. So from there, using those little basic pieces, this is how the actual system works. So you have what's called layer 1, which is the actual physical transportation. And then these are the data frames, so those packets. And then layer 3 is the actual routing on a network. So when you have one of these networks set up, you have in essence a computer at each one of your endpoints and start points. And then you have a switch in the center. And then you can send all of your audio distributed across the entire network, just like you would on a typical computer network. And the data frames themselves are the packets, things I was talking about. So that's kind of the basic overview. With all those things in mind, which I know is a lot, this is kind of the key piece in all of this. This is what makes all of it work. If you go back, I read the patent on the standard we use is called Livewire. There's another standard called Dante. But the thing that they all basically can patent is how they do this piece. If you think about it, if you think about having an ADC on some input somewhere, and then if you're sending packets out into a network, and then you're playing them out somewhere else on the other end, if you don't have you're not taking samples at the same time over here as you're playing them out over here, they're going to sit in line somewhere, right? Because you're sending a ton of data down the pipe, but then it has to get played out at the same time, or else it's taking up space. Basically, what happened is Axia, the company that makes this proprietary thing called Livewire, they have a patent on how they do their clock sharing. So they spit out clock packets on the network, and then all of the actual individual pieces on the network have to pick up the packet for the clock, and then they decide which one is the most sane or the most basically close to its clock, and then it uses that in a phase lock loop to reset its system clock. So in essence what they do is they're all perfectly time checked and time synced, so that as soon as a packet enters the network, at the same time all of them at the same play out a packet. So the buffers within the actual system are all extremely small, which is how they get away with super low latency. It's less than 10 milliseconds. It's for the most part unnoticeable, but which is really awesome for things like live broadcast, because if you think about it, if you're talking to a microphone and then it's going over the network, it has to come back in your headphone, and if it's delayed, you'll notice it, and it gets really distracting. So this is kind of the piece that makes it interesting and different amongst all the different things, because they're using the same standard, but they build this on top of it, and this is how they're differentiated at this point. The current proprietary audio over IP methods. CobraNet, which is the live audio facilities, stadiums, concert halls, things like that use CobraNet typically. It came out in, I think, 1995. It's one of the older ones, but that's kind of where it's caught on. And then Livewire is newer in broadcast facilities, and it has a really low latency, which is why they basically came out with this and didn't just use this. CobraNet still doesn't do the latency piece, but what makes CobraNet easier and different than Livewire is the fact that they basically don't have as much extra stuff packed onto their proprietary piece as Livewire does. Livewire does GPIO and a ton of different stuff. And then Dante. So Dante is what you're going to see in high quality recording studio environments. In studios, like a big studio where they might have 5 different individual studios, if they do network audio, they almost always use Dante. So if you know Focusrite, they're a big company that makes nice preamps and stuff, but they use Dante on almost all of their stuff. They just picked up Dante, because Dante's pretty good about making their stuff open and proprietary. So all that aside, why is this useful? Who uses it? ESPN, I had a chance to talk to, not ESPN, but the guy that does all the audio for CBS Sports at a convention I went to last semester. It was a radio broadcasters, a college broadcasters convention. If you think about it, sports audio is actually one of the more interesting spaces of broadcast audio, because if you sit down and look at one of the big charts that they have for all the different people that need to use a mic, there's a lot. For instance, you obviously have the announcer, the sports announcer, and there might be 2 of those, but then you also have comms between all of the cameramen and all of the producers. It does not make any sense for them to run big audio snakes out everywhere, because it's really hard for them to do that, because every stadium is different. So what they'll do is they'll literally take a Wi-Fi router and plug a cable into it and then share their audio network. And then all the cameramen have little belt packs that are Wi-Fi shared as well, so wherever they move, they're completely wireless. They use Livewire and they use Dante. So they use Dante for different things, but they use Livewire for all their sharing for comms mics. And when they pull up the trucks, they literally have a semi-truck trailer that's just dedicated to basically the audio over IP systems. And they use Ethernet patch cords. So that's one of the other interesting things, is all of these cords in here aren't traditional quarter-inch or XLRs. They're all little RJ45 Ethernet patch cables. So this is one of the big areas that's sort of come on. FM broadcast studios. So one of the cool things obviously is that You only have to run one cable between all your studios. Also, the way that most FM stations have set up their networks is, for instance, like at the radio station, the way our sort of chain of command works is if you completely obliterated our like main on-air studio, if you unplugged everything, because you have all this audio system built on computers, it picks up different sources. So if you kill like the main on-air studio, it can notice that, and then it can literally just pick up another thing on the network and stick it out on the FM transmitter. So that makes it a lot easier because you don't have to set up relays and you don't have to set up sensing systems. You can literally hard code it in like Python, and it'll just act when it needs to. So that's one of the sort of simple ways that it happens, but a lot of companies are coming up with ways to literally have like self-healing audio systems, which are just really crazy and bizarre to me to think about. So that's FM, and AM uses it too, but AM's kind of going away a little bit. So then also big production studios use it. So XM Radio is one of the obvious ones, and Microsoft actually too. I didn't realize this, but Microsoft has a huge production facility in Washington, where basically they do like live, all of their like tutorials, and anytime they pay people to do that, they have a whole production team that works behind those people to make those videos, and they have one of the biggest audio over IP installations in the country. One of the cool things about audio IP, aside from the fact that you can use it all on a network, is it saves a ton of rack space, because you can use little like 1U box and processor things and then just daisy chain them on a network, and you can basically like shrink down the size because you don't have to use as much processing. So the guy that I talked to that was affiliated with XM did all the processing for them, and he was telling me that basically what they do now is, since it's all digital and it's all controlled via like a laptop, one of their big problems is that they have a very limited bandwidth between what they can actually beam up to the satellites that get distributed back over like the world. So they have to be really careful about how much bandwidth they allocate to each one of their individual channels that gets beamed up. So what they do now literally is they sit in like a car in the parking lot outside of their server farm, and they can dial down the bit rate and the sample rate of their incoming signal to save bandwidth. And they just basically do that until people start complaining, and they move it up like a notch. And then wait and see what people do. And if no one complains, that's where it sits. It's kind of incredible because they give you perspective. Like, I mean, obviously satellites aside, but if someone did that in the FM world, you need to basically go into a room and find all the dials that you want to change and go in and change them all until you had what you thought your size was. And now they literally just sit in their cars and do it. So it's very different in the way that that approach has become. It's also very interesting because it's all in the digital domain now. So like you have the ability to do stuff like that, and it's much easier. So that's another place that is showing up. And the more interesting one, I think for me, because it's kind of cutting edge, is cars. Cars use this thing called the MOST bus, which is actually like a fiber bus. It's an optical bus. You can use the same standards on top of the fiber bus because it's in essence the giant network. Tesla is doing this in their cars. They're using, I think it's called MADI, but it's an audio over IP standard. But they're using it basically to pipe audio around in the car. And they're also using it for things like video, and they're using it like to do sound link to video. So for instance, if you want the car to listen to your surroundings, it can do that. And I don't know what like logic it does to that, but it can do it. Also like the listening to you, so if you do voice commands, they use a lot of audio over IP standards for that. Kind of interesting because it's starting to catch on there, and because the audio manufacturers have a lot of money, they do a lot of interesting research with it, which makes the standard better in turn. Basically it for what I had.